Good afternoon everyone, welcome to the channel. In today's video I want to talk about data augmentation and how we can train a neural network using data augmentation. And this is just another CNN video, and I am not typing up the code from scratch. I have time limitation today. So today we have two files. So this is the first file. It says Flowers102 WTA. WTA means without data augmentation, and this is the second file. So this is Flowers102 TA. So here data augmentation has been used for training a CNN. So I will switch between the files quite a few times, so just look at the name if you get confused. So let's start with this one. The workflow is similar to all the other CNN videos that I have made in the channel. You will already find 5 or 6 videos that I have made previously based on CNNs. So at first we need the libraries. So these are some of the torch vision and PyTorch libraries that are necessary for creating and training a CNN. So we imported some libraries, then as usual we need to define the device, which is either CPU or GPU. So I have GPU available. Then we apply transformation where we convert the PIL images into torch tensors, and here I have also used the resize function because the dataset that I used for this example is called Flowers102 dataset, which is a dataset of 102 different types of flowers, but they do not have the same size. So I resized them to this resolution 500 by 500 pixels. And this dataset is a little bit weird because here you can see 1020 samples in the training dataset, 1020 in the validation, and but 6149 in the test dataset. So this is opposite kind of scenario. Usually we have more samples in the training set and less in the test set. So what I have done is basically I used the test samples for training the model and concatenated training and validation set here using the concat dataset function from torch vision, I guess. Oh no, sorry, torch utils data. And so after concatenation 1020 plus 1020 it becomes 2040. So this is now my test set, and my training set is the original test dataset. And these two lines, I have a text file which contains the class names of 102 different types of flowers that this dataset has. I have converted the text file into a list using these two lines, and here we can see the first sample of the train set. So this one, and this 0 means first sample, and this 0 means the tensor values. If we use 1, then we can get the label, not the class names. For class name we have to use this one. I haven't shown the label here, which is not necessary, so I will come back to this one later again. So here I have shown as usual 10 randomly selected samples from the 10 train set. We can see different types of flowers here. So this is called thorn apple, primula, monkshoot. These are unusual names to me. Okay, some other examples. Same for test case, camellia, another monkshoot. Okay, so this is also monkshoot, this is also monkshoot. Then lotus, I know this one. Okay, then as usual after loading the dataset we have to define the data loaders. So I have selected a batch size of 30 and I have used drop plus true for train case because it has 6049 samples, which is not divisible by 30, but 2040 is divisible by 30, so I didn't use drop plus true here. Then a typical CNN architecture that I have constructed, it has two parts. This is the feature extraction part. Then at the last layer of feature extraction, we flatten the features so it becomes a single vector. Then we use a fully connected network, which is the classification part. So final output is 102 because of Flower102. Now here we have shown the summary of this network. Nothing new here. We have already shown these steps in the previous CNN video. So then a train batch for the train dataset, a test batch for the test dataset or data loader, whatever you want to call. Then we have an accuracy function. Since this is a CNN, we do not use this for autoencoders. Then we instantiate the model here, then set up the loss function, cross entropy loss for multi-class classification, and now optimizer I used Adam optimizer with a learning rate of 0.001. Then I trained a CNN. It takes quite some time, I think more than 30 minutes. Then I printed the results after every 10 epochs and trained the CNN for 50 epochs. Okay, so you can see after 10 epochs the train accuracy is 56%, test is 35. Then train increases rapidly and becomes 99% after 50 epochs, but test accuracy is around 52%, which decreases from 40. So from 54 it goes down to 52. And if you look at the loss as well, test loss suddenly increases towards the end, but train loss keeps on decreasing. Okay, then I plotted the loss curves and accuracy curves. You can see, so the red one is train loss, it's going down, but the test loss starts increasing, and accuracy also there is plenty of difference, so 52 and 99. So test accuracy is slightly more than half of train accuracy. Then I also showed some model prediction, which will not be good because we have only 52% of test accuracy. Okay, so I have shown randomly 12 samples here, and among these 12 samples I got 1, 2, so these blue ones are corrected predictions, 1, 2, 3, 4, 5, 6, 7. Okay, 7 corrected predictions and 5 wrong predictions. So this is actually 𝐂𝐨𝐧𝐯𝐴 flower. It's predicted as 𝐂𝐨𝐴 as well, but for this one, this is pincushion flower, but it's predicted as Mexican petunia. Okay, so this is how a CNN model looks like. Now, since this is Flowers102 without data augmentation, so I didn't use any data augmentation techniques in here, and you can see that this model overfits. So if you search the definition of overfitting in Google, then you will see something like the model performs very well on the training data but fails to generalize in case of unseen data, which means test data, because the model doesn't learn anything from the test data. And yes, we can see that. So if you notice this kind of behavior of the loss curves where test loss suddenly starts increasing after some time, but train loss continues to decrease, then you can understand that this is overfitting. So data augmentation is one technique which can reduce this overfitting issue. So this is without data augmentation. Now I want to move to the second file. So this is same code, but I have some change in this cell. So let's go again. So here you can see I have only transforms.resize and transforms.toTensor, but here I have added 3 more lines, and these 3 lines are basically some data augmentation techniques have been applied here, and I am only applying it to the train dataset. I am not applying it to the test dataset. So here what I've done is, if you look at transforms.randomaffin, here there are 3 parameters. So these degrees, this is the minimum, 3 degrees, and this is the maximum. So this will do some rotation to our original images between 3 degrees to 5 degrees randomly. Then this is translation, means horizontal and vertical shifting. So this is shifting and this is rotation. I have used like 5% horizontal rotation, 5% vertical rotation, and this is scaling. So scaling, what it does is it either enlarges or shrinks the original image. So here it will actually enlarge the original image, because after rotation there are some blank pixels usually, and I have tried to minimize those blank pixels by enlarging the rotated image. So here scaling, translation and rotation are tracking values. Then I have used flipping, both horizontal flipping and vertical flipping. This is probability 40% and vertical flipping 20%. So basically 5 types of data augmentation techniques has been applied in these 3 lines. There are more. I think there are something like color jitter or Gaussian blur, etc. So I only used 3. So this is the only difference here, and everything else in the code is same. I think I need to address this. So since, as I said, I am using test samples as train dataset because they have more images, so I applied train transform, which contains data augmentation, in the test dataset, and test transform for training and validation dataset. Then obviously I concat the validation and training and use the test images as train set. So that's basically the only difference. Then I also said that I will come back to this one. So let's look at this without data augmentation. So we can see the flower is pointing, how to say, towards the left, I guess, towards the left it's pointing, and you can see some part in the bottom. Now let's look at this one. Here you can see this one actually looks slightly bigger than this one because of where is it? Okay, so you can see the scaling here. So this does enlargement to the original image. So you can see now the flower appears slightly bigger here. So all the combined effects will have, so this will face the combined effects of these 3 lines. So I also said that it will have an horizontal flipping 40% of the times, not all the time. So in this case we don't see that, but randomly sometimes this will happen, sometimes this will not happen. So sometimes this will be vertically flipped, so this part will go to the top, and etc. etc. So randomly different changes will happen. And so this now in this case in this instance we can see that this is just enlarged and vertical flipping didn't take place, horizontal flipping also didn't take place, because the percentage is not 100. If it's 100 then it will take place every time, but the percentage, if it is not 100, currently it's 40% and it's 20%, then let's say 40% means 2 out of 5 occasions it will be horizontally flipped, and 1 out of 2 occasions, sorry, no, not 1 out of 2, 1 out of 5 occasions this will be vertically flipped. So 1 out of 5 you can consider it 5 epochs, 2 out of 5 you can consider it 2 epochs. So in 2 epochs this will be horizontally flipped, and in 1 out of 5 epochs it will be horizontally flipped. That's what this probability value means, and this will be applied every time. This has no probability, it has just the range. This is minimum, maximum. Sometimes the degrees will be 3, sometimes 4, sometimes 5, and like that. Okay, and so everything else is similar. Only difference we will see is in the results. So let's say after 10 epochs the train accuracy is 45%, and in this case we saw that it was 56 and test was 35, but here we can see test is still 35 but trend reduced. Then increases after 50 epochs it is 81, and without data augmentation we got 99, and it was 52, and with data augmentation we can see it is 61. And if we look at the curves, you can see the gap has reduced. Here there is a massive gap, here the gap is very much reduced. This gap is not very small but definitely smaller than this big one. Okay, and model prediction we got 1 2 3 4 5 6 7 8 9 9 correct out of 12. So I think we got 3 wrong. So we also getting few more correct predictions when we are randomly predicting, because the accuracy is 61% here and it was 52% without data augmentation. Okay, so one of the advantages of data augmentation is that it reduces overfitting, meaning that this situation doesn't occur where after a certain time the test loss continues to increase but train loss continues to decrease. Here we can see that both are decreasing. If you look at the values of 2.5 then all the way up to 1.47, but that's not the case here. 2.45 then it decreases, then suddenly increases. In these two lines the loss, in fact in these 3 lines the loss starts to increase. Test loss, I mean, I think train loss is decreasing. Yes, train loss is decreasing. Yeah, so I think basically that's it for this video, and I think I need to confirm one more lines. So you may also read this line in internet where it says that data augmentation increases the size of the data. Well, in this case it doesn't, because I'm not saving the images in an external folder. I'm just applying the augmentation tricks and it changes the diversity of the input. So the orientation changes. But if you want to increase the size of the dataset, you have to save. After applying augmentation, you have to save the images to external folder, then use the increased dataset for training the model. So but since I have used a Dodge Vision built-in dataset, I haven't done that. It's just diversifying my dataset. So in this case, it doesn't increase the size of the dataset, but only the diversity was side. But the size can also be increased if you save the images in external folder and increase the training dataset from 6149 to something more like 12,000, 14,000, something like that. Then I think you will get better results than this. You will get more accuracy in the test. Okay, so that's the end of this video. Thanks for watching.